If you were asked to sketch the absolute value function shown here, you're going to need to account for all these different transformations that are applied to the absolute value function, and we'll show you how to take them one at a time and get a good sketch that represents this function. So the first thing we need to remember is that this is the absolute value function. So it's based on f at x equals absolute value of x, and we know the parent function. We know what that looks like. And if I just I guess pop over onto the graph here and see what the parent looks like, we remember that it had a point right at the origin, and then it was over 1, up 1, over 2, up 2, etc., etc. Nice straight line. And it made a kind of V pattern because y was not allowed to be negative. Okay, so that is the absolute value function of the parent, and we just had a straight arm going up in this direction and a straight arm going up in this direction. Okay, so what has happened with this new function? Well, what do we see going on inside it? Well, a couple of things. At the front we have 1/2, and that is going to be a vertical compression. Inside the absolute value signs, we have a negative x minus 2, and then at the end we have a minus 5, and that's going to be a vertical translation or a movement down. So the whole function is going to be moving down. First thing we need to do, however, is we need to take a peek inside here, and we need to address the issue of there being a sign affixed to the x. And if we see any sort of negative sign or any sort of value attached to the x, the first thing we're going to want to do is we're going to factor that out. So this is going to be 1/2 and then absolute value of negative bracket and then x plus 2. There's the absolute value, and then minus 5. Okay, so notice that the negative, or the subtract 2, has now flipped to positive 2, and that makes it very easy for us to now identify that this horizontal translation or movement is actually going to go to the left by 2. Remember, if it's inside associated with the x, it's the opposite of what it appears. So positive 2 kind of looks like it will go to the right. It's actually going to move to the left. This minus 5 on the end is going to be a vertical translation down. Okay, let's take a look over here at the front, and we've got a 1/2, and that is going to be a vertical, so upwards, but it's going to be a compression of 1/2. So it's actually going to squish this parent function in the vertical direction. It's going to squash it a little bit, so it's going to be looking a little wider. The minus sign in the inside the absolute value functions, well, this is where you would normally find a horizontal mirroring, but you can clearly see the shape of the absolute value function. It's a V, and if we were in fact to mirror this horizontally, it would just mirror right back onto itself. So this mirror effect isn't going to have much of an effect at all. It would essentially take the points, like this point here, and it would just mirror it over onto the other point and vice versa. So I don't expect to see a whole lot going on with this mirror effect. Okay, so how do we get started? Well, the first thing we're going to do is we're going to make sure that we plot the new anchor point. So right now, the anchor point of the parent was at 0, 0. The new anchor point has moved to the left 2, so the minus 2, and then down 5. So I'm just going to go 2 and then down 1, 2, 3, 4, 5, and I'm going to put a new anchor point right there. Okay, now normally we would be putting in other points by just going over 1 and up 1, over 1 and up 1, over 1 and up 1 to get this V shape. But we can see that in the y direction, we are only allowed to go up a half of what we would normally go. So this is the compression. So in the x direction, there's a 1 here. There's no compression or stretch in the x direction, so we just follow the standard stepping pattern that we would. What does this minus sign do? Well, it would mean this. Typically, if we want to consider this right arm here, so let's just think of the green arm being this side up here. If I was just to worry about those green values, then instead of going over to the right one and then up a half, I would go, this negative value is going to tell me, well, go in the opposite direction. So I would go to the left one, and then the vertical compression only allows me to go up a half. So I would go over there, and I'll just show you where it would go, is right there. Okay? Then again, I would go over one and up another half, over one and up another half, and then over one and up another half. Okay? Now, what about the yellow arm? Well, this yellow arm, normally I would get there by going to the left one and up one, but now because of the horizontal mirroring, instead of going left, I'm going to go right. So I go to the right one. The blue compression only allows me to go up a half, over, up a half, over, up a half, over, up a half. Okay? So there is the new function. So the transformed absolute value function is right there. You can see that it has been translated to the left and down, and you can also see that this 1/2 at the front has vertically compressed the function. It has kind of squished it a little bit, and you can see that in fact it does look wider. Okay, if we wanted to check our table of values just to make sure that we've got everything right, I could go ahead and create a table of values with an x and a y. I could put in values that I know exist in the parent function. So there is a -1 and a 1, a 0 and a 0, and then a 1 and a 1. I could then take the x and the y values independently and apply the transformations vertically and horizontally. So, all right, let's start with the x values. The horizontal mirroring, or this reflection here, needs to happen first. So I'm going to multiply all of these x values by -1, and I get +1, 0, -1. Then I'm going to apply the red shift to the left of 2, so I'm going to subtract 2, and the 1 becomes a -1, 0 becomes -2, and -1 becomes -3. All right, let's consider the y. Well, the first thing I'm going to do with the y is I'm going to apply this vertical compression. So I'm going to multiply everything in there by a half. So 1 times a half is a half, 0 times a half is 0, and 1 times a half is 1/2. Then I move everything down by 5. So subtract 5 from each of these values. 1/2 subtract 5 is -4.5. 0 subtract 5 is -5, and 1/2 subtract 5 is -4. Oops. Is -4 and 1/2. All right. Well, are those points actually on the graph? Can we see them? Well, let's take a look. The points that would be on this new transformed absolute value function are, we've got -1 and -4.5. We've got -2 and -5. And we've got -3 and -4.5. And that is pretty sloppy. There we go. Okay, so let's just check and see if these values actually exist on this new point. -1 and -4.5. So there's -1 and -1, 2, 3, 4.5. That point right there. So that is on. -2 and -5. Well, there's -2 and down to -5. That's that anchor point. And -3 and -4.5. You'll find that that is that third point, and that's perfect. So there's how you can take an absolute value function and you can apply transformations. Just be careful again, if you see inside with the x, if you see a negative sign or a number attached to the x, make sure you take care of that first with some factoring, and you won't have a problem.